How old is the universe? A new study says it's much older than we thought. A team of astronomers recently analyzed data from the Planck spacecraft to come up with a new estimate for the age of the universe. 26.7 billion years, nearly twice as old as previously believed. Measuring fluctuations in the cosmic microwave background, a relic of the Big Bang, allows scientists to model key parameters about the universe's history and composition. This latest number provides an even more precise constraint on the age of our universe. Coming up with an accurate cosmological age has been a quest for astronomers since the early 20th century. While 26.7 billion years might seem significant on cosmic timescales, the study reinforces our understanding of events occurring in the early universe, like the formation of the first stars. The most widely accepted age for the universe is around 13.7 billion years old. But arriving at this figure has been far from straightforward for cosmologists. In the early 20th century, calculations relied on estimating the ages of the oldest stars in our galaxy, but these stars appeared older than the age derived for the universe itself, an obvious paradox. More rigorous age estimates came in the late 1990s, after scientists measured ripples in the cosmic microwave background radiation using satellites like COBE and WMAP. These tiny fluctuations in the afterglow of the Big Bang provide a snapshot of the early universe. By modeling the expansion and evolution of the universe from this data, researchers determined the universe was 13.7 billion years old, with an uncertainty of about 1%. But some findings have still challenged this view. Observations of galaxies in the early universe show mature galaxies already assembled when the universe was less than 1 billion years old. And measurements of the Hubble constant, which determines the expansion rate of the universe, have disagreed significantly. This implies different ages for the universe. So while 13.7 billion years is still the standard estimate, mysteries remain about the early formation of cosmic structures. The age also depends on complex cosmological models and measurements that continue to be refined. Determining the precise age may rely on new physics and advancing beyond our current understanding. For now, the best that astronomers can do is measure the cosmos in innovative ways and incrementally improve the uncertainty. This new study represents the best estimate so far by squeezing out a bit more precision, but the age of 13.77 billion years is unlikely to be the final word. Recently, physicist Rajendra Gupta proposed an alternative model that drastically extends the age of the universe. Gupta suggests combining two existing theories, tired light and Lemaitre's interpretation of cosmological redshift. The tired light concept was first proposed in 1929 by astronomer Fritz Zwicky. It posits that light gets tired and loses energy over huge cosmic distances, causing the redshift we observe in faraway galaxies. However, this theory came into conflict with observations. The brightness of supernovae does not decrease with distance, contradicting tired light. Gupta reconciles this issue by keeping tired light, but adding Lemaitre's view that space-time itself is expanding over time. In this unified model, redshift has two components, one from tired light and one from cosmic expansion. By reinterpreting observed redshifts this way, the model extends the timeline for galaxy formation after the Big Bang. Specifically, Gupta calculates it takes galaxies about 16.7 billion years to form and evolve, not the few 100 million years predicted in the standard model. Factoring in the age of the oldest stars, his model arrives at an age of the universe around 26.7 billion years, nearly double the accepted 13.7 billion. While thought-provoking, Gupta's proposed model lacks sufficient evidence compared to the well-tested standard cosmology. The study also raises concerns, requiring faster-than-light expansion in the early universe. Nonetheless, radically different perspectives further scientific discourse and motivate new observations to test hypotheses. Estimating the true age relies on scrutinizing theories against accumulating astronomical data. Gupta's ideas underscore how much we still have to learn. The fundamental forces of nature are determined by values called coupling constants. These define the strength of interactions between particles like electrons and photons. Constants like the fine structure constant are measured in the present day. But what if they were different in the past? This was the radical proposal of physicist Paul Dirac, who suggested coupling constants might gradually change over cosmic timescales. Allowing constants to evolve has major implications. It would alter things like the fusion rates in stars in the early universe, and recent observations from the James Webb Space Telescope challenged the standard model. It spotted early galaxies that appear too mature for their age based on current physics. But some theorists suggest this puzzle could be resolved if coupling constants had different values billions of years ago. With weaker interactions, clouds of gas could agglomerate into structured galaxies more quickly after the Big Bang. While speculative, varying constants illustrates how cosmology involves not just astronomical data, but also our understanding of particle physics. Theory and observation remain in tension when it comes to the early universe. But reconciling them may require being open-minded to non-standard ideas about the laws of physics in deep time. The age we determine depends directly on the model of physics we apply across cosmic history. The cosmological constant was introduced by Einstein over a century ago when he was seeking a static universe. This mathematical tweak to his equations was considered his biggest blunder, after observations revealed the universe is expanding. But the concept of the cosmological constant was revived with the discovery of dark energy in the late 1990s. This mysterious repulsive force seems to drive the accelerating expansion of the universe. The constant can represent the density of dark energy. However, physicist Rajendra Gupta has proposed a radical reinterpretation of the cosmological constant and what it represents. Rather than dark energy, Gupta suggests the cosmological constant quantifies the cumulative effects of the coupling constants changing over the history of the universe. The coupling constants define the strengths of the fundamental forces like electromagnetism and dictate interactions between particles. The theory of evolving coupling constants was first hypothesized by physicist Paul Dirac. If the couplings were higher in the early universe, as proposed by Gupta, this would have major implications. With stronger interactions, the early universe should have expanded extremely rapidly after the Big Bang. Gupta shows this neatly accounts for the surprisingly small sizes of galaxies observed by the James Webb Space Telescope in the very distant young universe. This resolves a puzzle regarding the standard model of cosmology. By revising the cosmological constant in terms of evolving couplings, not dark energy, Gupta is able to model an early universe consistent with James Webb observations and allow for an older age. While controversial, Gupta's theory illustrates how innovating on even basic established concepts like the cosmological constant can lead to new models addressing tensions between theory and observation. Rethinking assumptions opens possibilities for understanding outstanding questions about the universe's age and evolution. While this new estimate extends the age of our universe, the implications are far-reaching and require further scrutiny. If substantiated, an older cosmos allows more time for the emergence of structure and life. But current physics may need revision to explain early galaxy maturity. Upcoming missions will provide observations to test cosmological models. NASA's Roman telescope will precisely measure the expansion rate, and Europe's Euclid satellite will map millions of galaxies. Particle accelerators can also check conjectures of evolving constants over cosmic history. We must continue pushing the frontiers of observational and experimental cosmology. An accurate universe age remains elusive, but each refinement brings us closer to truth, illuminating mysteries of our cosmic evolution. Scientific progress involves building models, probing their limits, and seeking better ones as new discoveries emerge. We must remain open-minded about modifying even long-held assumptions. While daunting questions remain, humanity's quest to understand the cosmos and our place within it continues. Measuring the age of our universe is a profound quest spanning decades of cosmology. While the estimate has converged to 13.7 billion years, Mysteries endure about the formation of early galaxies. New observations may require rethinking underlying physics like constants evolving over time. Alternate models have been proposed to radically extend the cosmic timeline, but the standard cosmology has proven robust so far. As instruments achieve sharper resolution and theories grow more creative, our comprehension deepens. But the lifespan of the cosmos remains shrouded in uncertainty. This age may yet surprise us when viewed through the lens of future understanding. The unfolding story of our universe inspires awe and highlights science as an endless process of discovery. Let us continue unraveling cosmic secrets through bold imagination and tenacious inquiry. The adventure is just beginning.